Let's explore efficiency and conservation at home so that we can understand how to save energy at home. Energy efficiency and conservation are oftentimes confused. They're related, but they're different. Energy efficiency is the amount of useful energy you can get out of a system. In theory, a 100% energy efficient machine would change all of the energy put into it into useful work. However, converting one form of energy into another form always involves a loss of usable energy, usually in the form of thermal energy. In fact, most energy transformations are not very efficient. The human body is no exception. Your body's like a machine, and the fuel for your machine is food. Your body is very inefficient at converting food into useful work. Most of the energy in your body is released as thermal energy. When we're discussing how we use energy, efficiency refers to the equipment or machinery that we're using. For example, washing machines all clean our clothes. However, some are designed to do so using less water or electricity than similar machines. Clothes come out clean from both machines, but one machine is more efficient in its way it cleans them. Not to be confusing, but conservation of energy and energy conservation are not the same thing. One is a universal governing law of science. The other is a term explaining behaviors we employ to use less energy. When discussing how much energy we use, conservation refers to how we behave while using that energy. For example, the owners of the most efficiently built home can still waste energy if they leave the lights on and the refrigerator door open while pouring a glass of milk. People who have older, less efficient appliances, however, can still save energy by using them wisely. So essentially, energy conservation refers to the things we choose to do that use less energy. Turning off the lights, wearing a sweater, closing the door. Buildings are designed to keep the indoor air separated from the outdoor air. Otherwise, whatever form of heating and cooling system you have is trying to heat or cool the air outside the building as well. When your parents yelled at you for air conditioning the outside, they weren't wrong. That would be terribly inefficient. Buildings are constructed out of materials that insulate or block thermal energy transfer. Insulating materials do not conduct thermal energy well. Since it does not conduct the thermal energy, it traps that thermal energy, kind of like a thermos or Yeti mug. The parts of the building that separate indoors from outdoors construct the building envelope. The walls, floor, roof, doors, and windows are part of the building envelope system. Their purpose is to keep the interior of the building a comfortable, healthy place to work or learn while allowing access into and out of the building. It's easy to trap air when you have a fully closed system, but when you have doors, windows, etc. opening and closing all day, it's hard to keep that air in one place. The space above the ceiling, below the floor, and within the walls is filled with insulation, which prevents thermal energy transferring. Insulation is graded by its R value, which is an abbreviation for its resistance to conduction. In order for the building envelope to do its job, air must not be allowed to flow into or out of the building. The most obvious way to avoid air infiltration is to keep doors and windows closed when the heating or cooling system is running. Doors and windows that leave gaps, even when closed, need a strip of weather stripping to seal those spaces. The space between doors or windows and the walls that contain them also need to be sealed. Immediately after a building is completed, the doors fit snug in their respective spaces. Over time, however, the building expands and contracts slightly as it heats and cools with the seasons, and the doors may not fit as tightly anymore. Therefore, it's important to inspect these junctions annually and fill any gaps with weather-tight caulking. Many buildings, such as schools, apartments, and condos, have two sets of doors at each entry point. These vestibules prevent large amounts of air from rushing in or out of the building as people enter and exit. To work properly, though, both sets of doors need to be kept closed when they're not being used. You can test the envelope of your home by putting a dollar bill in your door. If it slides out easily, your door may need some insulation. Weather stripping makes that seal nice and tight, so when I put the dollar back in, it sticks. Windows made of metallic frames were often used in buildings built in the 1950s and 1960s. The aluminum in the frames is an excellent thermal conductor and will conduct energy right through to the other side, breaking the seal of that building envelope. As you can well imagine, this is not a great material for constructing window frames. Most windows today are made of vinyl, wood, or composite materials that are better insulators. Low E glass has a special reflective coating that reflects ultraviolet light. Ultraviolet light that can come through is trapped in the space and transformed into thermal energy. Think about the inside of a car on a hot sunny day. If light reflects off the window, it can't transform into heat and can't be trapped inside the car, or in this case, your house. The number of panes of glass in a window is important too. Single pane windows are not well insulated. Double or triple pane glass has an insulating space between the glass that allows light in and keeps thermal energy from transferring across the window. This space is usually filled with air or other gases that create a big insulation barrier between the inside and outside. If you ever feel air moving through the area around a window on a windy day, there may be small gaps in the window materials. Weather stripping and caulk can often be used to patch these gaps and seal that building envelope right up. To count the number of panes in your window, you can hold an object and count the number of reflected images. In this case, there's 2 images, so there's 2 panes of glass. That means there's a gap of air in between to help insulate the inside and the outside. The electronic devices that you use at home are consuming electricity, just like a car consumes gas. Schools and homes contain many electrical devices called plug loads that help you complete tasks, learn, or help occupants stay comfortable and safe. It's estimated that about 30% of the total electricity consumed by a school is used to power these electrical devices. Managing the use of such equipment can greatly reduce a school's electricity consumption. Many computers, TVs, DVD players, and other electrical devices use electricity even when they're turned off. This type of electricity consumption is known as a phantom load because it can easily go unnoticed. Phantom loads are also known as standby power or leaking electricity. Phantom loads exist in many electronics or electrical devices found around the house or school. Equipment with electronic clocks, timers, or remote controls, portable equipment, and office equipment with wall cubes all have phantom loads and consume up to 40 watts when turned off, depending on the device. Especially when they're massed together, these appliances should be plugged into surge protectors so that all of the power can be turned off when they are not being used. When shopping for a new appliance or lighting, look for the ENERGY STAR label. It's your assurance that the product saves energy. ENERGY STAR appliances have been identified by the U.S. Environmental Protection Agency and Department of Energy as the most energy efficient products in the home or classroom. Another way to determine the efficiency of appliances is to compare energy usage using ENERGYGUIDE labels. The federal government requires most appliances to display bright yellow and black ENERGYGUIDE labels. Although these labels don't say exactly which appliance is the most efficient, they provide the annual energy consumption and average operating cost of each appliance, so you can compare them yourself. To make it easy to compare appliances, all of these distinctive yellow signs are organized exactly the same way. The ENERGYGUIDE tells you what the appliance is and lists key features, including similar features across other models in the price range. It lists in more detail what the make and model of that appliance are. This sometimes includes different capacities and sizes. The initial price isn't the only price you pay, so the ENERGYGUIDE tells you the cost of running that device for a whole year based on average consumption and average energy costs. This cost range compares your appliance's estimated yearly energy cost to similar models. The cost range gets more specific when you look at more specific features. This makes comparison shopping a breeze. The energy cost is directly related to the consumption, or the amount of kilowatt hours. This estimated yearly electricity use tells you how much power, kilowatts, you've used over time, hours. The ENERGYGUIDE provides information for all appliances, not just energy efficient appliances. However, you can still look on the ENERGYGUIDE for the ENERGY STAR certification stamp. This appliance is ENERGY STAR certified, so it's more efficient compared to other models. This explains why when you look at the cost range for the annual yearly energy cost, this particular model is on the lower end of the range. A lower annual cost for energy means you're using less energy, you're being efficient, and by purchasing this model, you're making a conservative choice. Every machine that runs on electricity has an electric nameplate on it. The nameplate is usually a silver and black sticker that can be found on the bottom or back of the device. The nameplate has information about the amount of electricity the machine uses. Sometimes the current is listed. The current is measured in amperes or amps. Sometimes the voltage the machine needs is listed. The voltage is listed in volts. Sometimes the wattage is listed. The wattage or power is measured in watts. If the power isn't listed, the current and voltage are both listed and can be used to calculate the power. Often, the letters UL are on the nameplate. UL stands for Underwriters Laboratories, Inc., which conducts tests on thousands of machines and appliances. The UL mark means that samples of the machines or appliances have been tested to make sure they're safe. Carefully explore your home. You'll be able to find these nameplates on electrical appliances. They vary in style, but mostly they share the same information. To understand the information on these name tags and to measure electricity, we need to understand three big ideas. Voltage, measured in volts, is the electric potential difference between two places in a circuit. Voltage is the force that pushes along the charge. The current, measured in amps, is the flow of electric charge past a single point in a circuit. Power is the rate of time of doing work. A watt is a measure of the electrical power an electrical device uses. Most electrical devices require a certain number of watts to work correctly. Light bulbs, for example, are rated by watts. 13, 32, 60, 75, 100 watts, as are appliances such as a 1500 watt hairdryer.
I said take only what you need to survive.
It's my industrial strength hairdryer, and I can't live without it.
This refrigerator's nameplate does not have the wattage or power listed. If you can find the voltage in volts and the current in amps, you can calculate the power using this formula. We multiply the current times the voltage. The current was 6.5 amps, the voltage 115 volts according to the electric nameplate. When you multiply it together, this refrigerator required 747.5 watts. A kilowatt is 1,000 watts. A kilowatt hour is the amount of electricity used in 1 hour at a rate of 1,000 watts. Visualize adding water to a bowl. In this analogy, a kilowatt is the rate at which water is added to the bowl. A kilowatt hour is the amount of water added to the bowl in a period of time. Just as we buy gasoline in gallons or wood in cords, we buy electricity in kilowatt hours. Utility companies charge us for the kilowatt hours we use during a month. To calculate kilowatts, take your power in watts and divide it by 1,000. The refrigerator required 747.5 watts. Divide that by 1,000. To get kilowatt hours, you take your kilowatts and just multiply it by how many hours you used it. If it was used for 24 hours, because it's a refrigerator, in 1 day you used 17.94 kilowatt hours. Electric utilities use megawatts and gigawatts to measure large amounts of electricity. Power plant capacity is usually measured in megawatts. 1 megawatt is equal to 1 million watts, or 1,000 kilowatts. Gigawatts are often used to measure the electricity produced in an entire state, or in the United States. 1 gigawatt is equal to 1 billion watts, 1 million kilowatts, or 1,000 megawatts.
This sucker's electrical, but I need a nuclear reaction to generate the 1.21 gigawatts of electricity.
1.21 gigawatts! 1.21 gigawatts! Great Scott!
You can calculate how much it costs to operate the machines you use by using those nameplates. All you need to find is the wattage, the cost of electricity, and the number of hours a week each machine is used. You can estimate the number of hours the machine is used each week, then multiply by 52 to get the yearly use. Using this TV nameplate as example, we can see that it's used for 30 hours each week, and then we can find how many hours it's used per year, 1,560. This is because there's 52 weeks in a year. Remember that electricity is measured in kilowatt hours. You'll need to change the watts to kilowatts. 1 kilowatt is equal to 1,000 watts. To get kilowatts, you must divide the watts by 1,000. Using that TV as an example, we divide like this. So we end up with 0.18 kilowatts. The average cost of electricity in the U.S. is about 13 cents a kilowatt hour. You can use this rate or find out the actual rate from your electric bill. Using the average cost of electricity, we can figure out how much it costs to run the TV for a whole year by using this formula. We're multiplying the hours used times kilowatts. This gives us kilowatt hours. Kilowatt hours times the cost of electricity gives us our total cost to run the TV for a year. Plug in our yearly hours, our kilowatts, and then the cost of electricity per kilowatt hour, multiply it all together, and it costs about $36.22 to run this TV. Years ago, we used a lot of energy in the form of electricity to make light to be able to see. 30% of the electricity schools used was for lighting, and homes used about 14% of their electricity consumption for lighting. That's because homes, schools, and other commercial buildings used a lot of incandescent lighting. These inefficient bulbs were perfected by Thomas Edison in 1879 and didn't change much for the next 125 or more years. These bulbs were surprisingly inefficient, converting up to 90% of the electricity they consumed into heat, not light. Notice how not only does the bulb quickly heat up, the air around it seems to heat up. As the electrons pass through the filament, it superheats the metal, creating light. The resistance in the filament acts like friction against those electrons. The Energy Independence and Security Act of 2007 changed the standards for the efficiency of light bulbs used most often. As of 2014, most general use bulbs must be 30% more efficient than traditional, inefficient incandescent bulbs. What do the new standards mean for consumers? The purpose of the new efficiency standards is to give people the same amount of light by using less energy. This matches our definition of efficiency, which aims to do the same amount with less energy. Advancements in technology mean that we can see the same amount of light but not use as much power. We're using less energy over time. Most incandescent light bulbs have since been phased out and are no longer available for sale. This has resulted in significant energy savings for homes and schools. Newer, efficient lighting now accounts for 11% of the electricity used in schools, but only 5% used in homes. There are several lighting choices on the market that meet the new efficiency standards. Compact fluorescent light bulbs, CFLs for short, provide the same amount of light as incandescent bulbs, but use up to 75% less energy and last 10 times longer. CFLs produce very little heat. The bulb itself warms up, but the air around it doesn't heat up. The infrared camera is picking up thermal energy from the current that passes through the tube. Using CFLs can help cut lighting costs and reduce environmental impacts. CFL bulbs fit almost any socket, produce a warm glow, and unlike earlier models, no longer flicker and dim. CFLs have a small amount of mercury inside and should always be recycled rather than thrown away. Many retailers will recycle the CFLs for you for free. Light-emitting diodes, better known as LEDs, are gaining in popularity. Once used mainly for exit signs and power on-off indicators, improved technology and lower prices are enabling LEDs to be used in place of incandescents and CFLs. LEDs are one of the most energy-efficient lighting choices available today. LEDs use 75% less energy than traditional incandescents and have an average lifespan of at least 25,000 hours. The cost of LEDs has dropped in the last 5 years and may continue to drop. They use less energy than CFLs, save more electricity, and produce fewer carbon dioxide emissions. One LED bulb has several tiny LEDs inside of it. LEDs contain semiconductors like solar panels and other diodes. However, the difference is in the way the electrical energy is used by the LED. The U.S. Department of Energy estimates that widespread adoption of LED lighting by 2020 2027 would reduce lighting electricity demand by 33%. This would avoid construction of about 40 new power plants. Thanks to ongoing technological innovations, light bulbs keep becoming more and more efficient. They're able to produce the same amount of light with less energy. A better light bulb is only effective if people use them. Conservation is the behavioral choice to use less energy. You can choose to conserve energy by installing more efficient light bulbs. To help make that choice, let's compare different styles of light bulbs on an even playing field. Using this worksheet, we can compare the total cost and environmental impact of 4 different types of light bulbs. Let's start with a basis of comparison. Let's start by looking at incandescent bulbs only. Let's find the cost of just the bulbs. I want the bulb to last for 25,000 hours. 25,000 hours divided by the bulb's lifespan tells me that it's going to require 25 bulbs. Once we know how many bulbs it takes, we multiply that by the price per bulb. Incandescent bulbs are pretty cheap. That's why they used to be very popular. So we multiply the total bulbs times the cost, and we get $12.50. The bulbs may be affordable, but the cost of electricity will catch up to you. We take the total number of hours times the wattage, which is a measurement of power. We're going to look at that in kilowatts, so we're going to move that decimal over a few places. Multiply together, we get about 1,500 kilowatt hours for those incandescent bulbs. This is a measurement of how much energy we're using over time. Just like buying gas at the gas station, we're going to multiply our consumption by the price per kilowatt hour, which is about 13 cents. Multiply that together, it costs about $188.25. The life cycle cost of a bulb looks at the cost of the bulbs and the electricity cost. The individual bulbs are cheap, but you have to buy a lot of them. Because they're inefficient, they use a lot of electricity. We need to find our cost of bulbs and the cost of our electricity and add them up. This is the total cost for the life cycle of that bulb. In other words, this is what it costs to light light bulbs for 25,000 hours if they're incandescent. This is our life cycle cost that we need to compare to. All other bulbs are designed to be more efficient, but are they more cost efficient as well? Using the bulbs makes a dent in your pocket, but it also leaves a carbon footprint. Because of the way electricity is generated, for every kilowatt hour that you consume, 1.6 pounds of carbon is released. 25,000 hours of incandescent bulbs takes 1,500 kilowatt hours. Multiply that by 1.6, and that means we're looking at 2,400 pounds of carbon dioxide. This gives us another point of comparison. The other light bulbs are designed to be more efficient and use less electricity. So predict how that'll relate to the amount of carbon dioxide released in the process of lighting each bulb for 25,000 hours. Now that you have the comparison for the incandescent bulb, try these same calculations for all of the other different bulb designs. Compare the number of bulbs, the cost of those bulbs, the cost of the electricity, and the overall environmental impact of each bulb. Now that you've explored the impact that your energy choices make at home, it's time to think bigger. What if you were in charge of designing a home from the ground up? How would you design it to make more energy efficient? What conservation choices would you make? Next week, you'll get the chance to design your own model home in our Home Design Challenge. Your house will be judged on a few criteria. You'll have to follow some building codes. This includes the way the doors and windows are designed. Your house will have to be insulated. You'll have to design the home so it has a solid and impermeable building envelope. You're going to have the opportunity to shop for lights and appliances, picking out lights and appliances that might benefit the environment and your pocket. And then you're going to get the chance to decorate your own home. During our next session, you'll get the chance to start building your home, but this session we can start planning and brainstorming. Once you've finished your home audit, you'll have lots of information to help you understand the important elements of what makes a home efficient or inefficient. And then you're going to look at that audit information to make informed decisions so that you can start planning out your home. All of this information follows along with the slideshow that you have set up for all of the home audit, and it continues into the information for planning your own home model.